Hello, everyone. Today's lesson is on aquaponics. I think a lot of students really enjoy this topic. It's pretty cool. Um, I hope to teach you some nifty things about aquaponics today. Maybe some of you even are experimenting with aquaponics at home. I know it's a popular thing. It is a lot of fun, and I think offers some really interesting solutions for producing food. Let's get into this. Um, Typically, it's a combination of hydroponics and fish culture. So we'll kind of touch on some of the hydroponic stuff that we've covered already, and I'll cover a little bit about growing fish. I'm not going to get into a lot of the nitty gritties of the types of diseases and special nutritional requirements of certain fish. That's getting beyond the scope of this course, but I'll describe the system, the mechanics, some of the challenges that aquaponic growers face. Um, Certainly, as far as a market goes, people are looking for organic food. We know that. We've spent some time talking about it. There's definitely increasing demand for vegetables. We've seen that with vegetable farm growth in recent years. Um, and fish production is becoming really problematic. Plus, we know eating fish is good for your health, but it is very expensive. If you've bought fish at a grocery store, you'll know what I'm talking about. Um, so this sort of looking at aquaponics is an attempt to sort of address all of these things, right? Improve the efficiency of our energy use in making food, and also maybe reducing our impact on the environment in terms of harvesting fish from the ocean, for example. Um, Definitely, a lot of this stuff you're keenly aware of. There's plenty of people harping on about the challenges in food production. And we've talked a little bit about how greenhouses offer a lot of solutions to this. But um, anyways, aquaponics seems to be an interesting fit. Um, I don't know that the economics are quite there yet in North America, but in parts of the world, it does work. Um, Now, I've mentioned in the past the Green Revolution. There's a link there if you want to go to the website, but you can look up the Green Revolution yourself. That's kind of a misunderstood one. Remember, I talked about that's about the invention of fertilizer, the development of hybrid crops, basically, Green Revolution is modern agriculture, and how that had a huge impact on improving our yields. But we also know it's had an impact on the environment. Um, the Blue Revolution is kind of where we're trying to figure out how to make seafood in farms instead of harvesting it from the ocean. And I think we're in the process of figuring that out. Already, a lot of the salmon and trout you buy at the grocery store is farm raised. It's not wild. Where wild salmon is much more expensive and wild trout is much more expensive. So aquaponics kind of is looking at a way to improve on all of this. Uh, Aquaculture, which is fish farming, the picture in the bottom there sort of gives you an idea of what it looks like. Um, this is a photo. Actually, I got to see this farm in Scotland up off the coast, and it's pretty impressive. These are huge fish pens where they grow the fish out in the sea. But it has a lot of negative environmental impacts. So the fish that grow in these pens, because of their high density, can get sick, and then their disease passes on to fish that are in the natural environment. Plus, all the feces, the waste that falls out of the pens, even dead fish that are in there, the detritus causes a negative impact on the environment around the farm. So detritus, again, disease, oxygen reduction, um, impacting the health of natural predators. Uh, Unfortunately, it's not a perfect solution. So trying to do fish culture on land maybe helps us contain some of those things and reduce the runoff. Um, so essentially, you know, fish are fed food in an aquaponic system. So you add, it's almost like dog food to the water. The fish eat it, then they defecate and pee in the water, and that is the food source for the plants. Now, it can't just be fed directly to the plants, it has to be processed by bacteria to undergo what we call mineralization, and then the plants can feed on the resulting nutrients. And so you're growing both vegetables and leafy greens as well as fish. So that's essentially what aquaponics is. Fish food in, lettuce, and fish out. So as far as aquaponics goes, I think the most successful farms that I have heard of are in warmer climates where less energy is required and labor costs are lower. This is a picture from an aquaponic farm in the Caribbean that feeds people at a resort. Now, the economics are already skewed when you think about it, right? Because the people at the resort have a lot more money than the local economy. So again, it's wealthy people sort of supporting the development of this farm, but it's generating revenue and income, but not really at a stage where it's providing a real solution for food for local people in terms of economic cost. Um, the type of fish that you see in aquaponic systems ranges fairly widely, although the most common one is tilapia. Uh, that's this one down here. You can buy it in the grocery store here in North America. It's a fairly easy fish to grow. It likes warm water. It grows quickly, which is important. But prawns, which are kind of like a freshwater shrimp, are showing a lot of promise. A couple of the farms in North America that actually are profitable make most of their money off growing prawns, and these are down in South Carolina in warmer climates again. Um, the fish food that is the main input into the entire system is where your costs are, right? So you got to buy all this fish food and you got to feed the fish. Uh, it consists of protein, fats, there's phosphorus, there's potassium in there, bone meal, a lot of these things that plants need as well, right? And then there's vitamins and minerals that the fish need to keep them healthy, which of course also spills out into plants. So there is some compatibility as far as the nutrients go. Um, this is kind of a more detailed look at what a aquaponics farm would be feeding. So they're using floating tilapia food, and then they're supplementing that with dolomitic lime, which brings you calcium and magnesium, and carbonates, which we'll talk about later, which are important. And then they're also adding vitamins. They're in a bulk vitamin kind of powder, not unlike what you would maybe buy if you're buying vitamins for yourself. So there's iron, manganese, and zinc. Again, you see how there's some overlap for plants, right? And in our own experience at the college, our system's not up and running right now because the virus, the pandemic has kind of put a stop to that. But we find that we have to supplement with quite a bit of iron to keep the plants healthy as well as the fish. So that's an important one. So again, just summarizing some of the needs. You need iron for the fish and the plants. Calcium, we know we need for both the fish to grow proper bones, but the plants also benefit. And potassium, which of course the fish and the plants both need. And that can be supplied as potash, which is a mined from the ground fertilizer, or potassium hydroxide or chloride, which are basically derivatives of potash. So it's difficult to be outright organic on this, but we know from our experience that alfalfa meal can be used, but it's difficult to feed that to an aquaponic system. So when it get into the nitty gritties, aquaponics is organic, but again, we suffer from some of the absolute rules around organics, which makes it difficult to use things like lime and potash. But, you know, most aquaponic farmers don't have too much difficulty with people challenging them on whether they're organic because people are kind of happy they're at least trying to do something a little more sustainable. Um, Aquaponics, this is important, is not a closed loop. It's not like this sort of self-sustaining environment. It is an input and an output. So you put in your fish food and out comes lettuce or whatever and fish. So you're constantly adding into the system. So it's not what we call a self-sustaining ecological system, but it requires inputs. But at the end of the day, remember, I've talked about this, especially when you discussed permaculture, the idea that if you're constantly removing something from the system, there has to be something to make it up, right? So there's going to be inputs. So this idea of an infinitely self-sustaining environment doesn't work when we're taking away huge amounts of energy from that system to feed a lot of people. Some of the questions that arise discussing aquaponics, and they're legitimate, is what is in the fish food, right? And some of that overlaps with organic fertilizers we'll be talking about in your root zone course, so I'm not going to get into that. And also, what's the ratio, the nutrient ratio? So we've spent some time talking about nutrient ratios and how they impact plant growth. And as growers, we'd like to be able to control the nutrient ratios, but in aquaponics, we give up a lot of that control, which kind of parallels what I've talked about with organic production. Um, Water chemistry becomes very important in aquaponics, as we've already discussed in hydroponics. So as far as fish are concerned, they need sufficient oxygen, they need the right temperature, they need the right nutrients, and they need the right pH, and they need clean water. That all seems really obvious, right? And I think you'll see that parallels with the plants. So we have some good compatibility, right? Well, maybe not. Um, Plants have slightly different needs, so we have to make compromises. We'll get into this as we go through the lesson, but things like pH are different between fish and plants, um, and temperature. So let's have a closer look at this. As far as water quality goes, measurements are dissolved oxygen, right? That's a daily testing you do. We have a meter at the college that gives us dissolved oxygen. You measure the temperature, you measure the pH, and you measure ammonia content. We'll talk about that a little bit more later as we get into nitrogen. Um, Weekly testing, you do drip chemical tests for nitrates, nitrates, phosphorus, potassium, iron, alkalinity, which you've talked about with our bicarbonates, and hardness to make sure there's sufficient calcium for the fish. Um, let's look at oxygen. So as far as oxygen, it's critical for fish to breathe. That makes sense, right? Fish are aerobic like us. It's also critical for plants. We've talked a lot about respiration in roots. Um, it is also really important for aerobic bacteria, which are the ones that mineralize the fish food, the waste, fish waste, into plant food. So we need to make sure we have aerobic bacteria. That's probably the most critical out of everything. So oxygen is absolutely critical. So dissolved oxygen is measured regularly. As far as measuring dissolved oxygen, we need 4 milligrams per liter of oxygen, or 4 ppm. It's really difficult to get much more than 7 to 9 ppm at room temperature at sea level. A lot of times I chuckle when I go to the grocery store and they're selling oxygenated water. The chemistry of how gases dissolve in water is literally, you can't change the rules, right? So to oxygenate water, you cannot go above 7 to 9 ppm at atmospheric temperature and pressure. So if the water bottle is under pressure, like a pop can, then you can get more gas in the water, right? So when you open up a pop can, it cracks and you hear the pressure release. And what happens? As soon as you release the pressure, the bubbles start forming in the pop because the gas is escaping. So for a very short time, it will have maybe more CO2 in it, but it quickly evaporates. And the same thing goes for oxygen. Unless you're in a pressurized system, you cannot get more oxygen in. You can bubble as much as you want through. You're not going to exceed 7 to 9 ppm based on both temperature and pressure. The warmer the water is, the less gas it can hold. Okay, number of fish in the system is probably a big impact as well. Obviously, they're all breathing, and if you have too many fish in the system, they consume the oxygen faster than you can get it in. So that really is one of the biggest limitations on how many fish can actually fit in a system. But as far as oxygen is concerned, in aquaponics, what's interesting, once you get into the science of it, we actually spend more time focused on CO2 than we do oxygen. Primarily because carbon dioxide is way more water soluble than oxygen. I gave you the example of a pop can, cracking the pop can open. As soon as you crack it, it starts fizzing. Now, we've all drank pop, and you go to the restaurant, you know, by the time they take the pop from the fountain to your table, the pop's not flat. It's still fizzing. It takes some time for all the CO2 to escape. So, whereas oxygen actually escapes very quickly. If our pop was bubbled with oxygen, we would be flat before the waiter or waitress made it to your table with the pop. So carbon dioxide here, you can see, is 25 times more soluble than oxygen. So what we want is we want to make sure we want to get the CO2 out of the water. If there's too much CO2 in the water, it starts to impact pH, and it starts to impact the physiology of the fish. If you've ever done any kind of diving or anything like that, you'll also know that it causes acidosis, which can make you go unconscious. So we'll look at CO2 a little bit later, but let's look at temperature first. Fish like it warm, some like it cold. So tilapia is a warm fish. So in tropical climates, you'll see they're growing tilapia. In North America, we often grow tilapia indoors, but if you're outdoors, you try to grow trout. But trout need it very cold. So then you're looking at fresh, cold water or refrigeration, which is a lot of money in energy. Prawn generally like it warm. They're also very quick growing. And the shrimp industry, because they grow so fast, is actually, these are one of the ones where people actually seem to be making money. And restaurants will buy fresh prawns from aquaponic farms. So now plants typically, they like it cool because root respiration increases as the water temperature goes up. Because remember, the roots are dangling in the water, and we need to make sure it's not too hot. So summertime production or tropical climates, we have to be very careful we don't exceed temperatures. In our discussion about hydroponics, we talked about how NFT is cooler than deep water culture. And so often in tropical climates, you'll see NFT where they grow the lettuce and deep water where the fish are, obviously. But again, temperature is something that we got to keep an eye on to make sure we don't get root diseases or that we're not consuming too many sugars and limiting production of food in the plants. With CO2, I mentioned that fish and plants both produce carbon dioxide because they both undergo respiration. And CO2 is water soluble. Remember, it's 25 times more water soluble than oxygen. And when it enters water, it forms carbonic acid, which drops the pH. So we need to remove carbon dioxide. And what we typically do with aquaponics is one of the tanks has lots of air being bubbled through it. And a lot of times people look at them and say, oh, that's oxygenating the water. Well, it is, but really, actually, it's not a process of oxygenating. That's a byproduct. What we're really doing is degassing, and we're removing carbon dioxide. So when you see that vigorous bubbling that's happening in the tank, that's actually more removing carbon dioxide because we need to get that out of there so the fish are not impacted and the plants are not impacted and the pH stays correct. Looking at here, so CO2 and reacts with water to form carbonic acid, which quickly dissociates a proton. And it can also produce another proton, so two acids, and then produce carbonate ion. But these two are in equilibrium all the time when carbon dioxide is in the water. So if we can prevent the carbon dioxide from getting in the water by bubbling it out, we can reduce the production of acid in the water. Right? That's where all that bubbling, that's what it's all about. Right? It's all about reducing carbon dioxide in the water and reducing the production of acid. If you remember from our root zone course, we talked about how we want a minimum of 1 millimole of bicarbonate in the water. And this is the reaction we're talking about here. By having 1 millimole of bicarbonate, it buffers the pH. You end up with it sort of bouncing back and forth in kind of the right pH for plants. Plants and fish, the pH is a bit of a compromise, but let's say 1 millimole is the place to be. Now let's look at carbon and nitrogen in the system. This is from Plant Science 2. You remember this picture with the nitrogen cycle and the idea that the nitrogen in the atmosphere is moving through the soil, through bacteria, and coming back around full circle. And sometimes it's actually mineralized by bacteria, so nitrifying bacteria, into nutrients that plants can use, like nitrate. And sometimes denitrifying bacteria actually interrupt that process, and they convert the nitrogen back into nitrogen gas, and it's lost to the atmosphere. So in aquaponics, we want to spend a lot of time having the right environments, so enough oxygen, that we get the correct bacteria that will mineralize the nutrients, so we get assimilation, and minimize denitrification. So the more oxygen we have in the entire system, the better we will get nitrification happening. As far as carbon cycle, remember CO2 is in the atmosphere. Plants are assimilating it into sugars, and the roots are undergoing, and everything's doing respiration as well. So we have CO2 coming in. Some of it's being turned into sugars, and some of it's coming back out as CO2 in respiration. And that sort of cycles through the entire system. Looking closer, when you have sugars, or basically think of this as your feed going into the aquaponics. Some of it is broken down through respiration and digestion. That's what this is showing. And you get water and carbon dioxide, right? You breathe out your mouth, you get moisture and CO2 coming out of your mouth. That's from respiration. And then, of course, photosynthesis reverses that. Back, the CO2 gets incorporated into sugars, and oxygen is produced. But that's lost to the atmosphere in aquaponics. We can't capture that. So in the carbon cycle, we're looking at mostly the nutrients that are coming in the fish food. We're trying to get as much of it consumed by the fish to grow, and then the remainder is captured if possible or lost to the atmosphere as CO2. And what is caught produces oxygen through photosynthesis. The wrong bacteria, if we don't have enough oxygen, right, we get those anaerobic bacteria. They end up converting the fish food, that's the fish food, into methane and ammonium and stuff like that, things that are lost. They're not necessarily beneficial to the plants or the animals. So again, we really want to avoid anaerobic conditions. The nitrogen cycle, remember, we want aerobic conditions for nitrate to form, and we do not want anaerobic conditions because we get denitrification, which ends up producing nitrogen gas, and we lose it to the atmosphere, and the lettuce doesn't grow. So the theme here, what you should be getting out of all these slides, is that we need aerobic conditions. They're really, really important. So again, in the nitrogen cycle, this is just a bit easier to see. We want to avoid denitrifying bacteria. We want to make sure we have enough oxygen. And one of the problems in an aquaponic system is that the fish produce feces, and they're not necessarily water soluble. They settle down to the bottom of the tank, and they need to be captured and processed by bacteria. And unfortunately, I haven't seen any aquaponic system that actually shreds or tries to break up feces into really small particles so they stay in suspension. So a lot of the feces actually settle to the bottom of the tank. And as they settle, they create sediment that creates localized anaerobic conditions. And that's where we start losing efficiencies in the aquaponic system. So it's very difficult to get oxygen into those sedimentary parts, and so we get denitrification there. Also, if you don't have enough oxygen because of those anaerobic conditions, the plants will end up producing ammonium and ammonia, which is not the best thing for fish and plants. This is just a picture showing what sediment might look like in an aquaponic system. As it settles to the bottom of the tank, you'll see it piles up. And in the middle of that pile, you get anaerobic conditions. And those can be very deleterious to an aquaponic system. In fact, if you talk to an aquaponic grower, if they're looking at their lettuce and it looks like it's really nitrogen deficient, oftentimes somewhere in their system there's a dead fish. A decaying fish will get caught on the bottom, and as bacteria eat it, you get anaerobic conditions, and it actually consumes nitrogen from the water, and the lettuce will stop growing or even go yellow. So that means they have to look at their filters quickly, make sure there's nothing caught there. A lot of the aquaponic systems, when I look later in this lesson, I'm going to go through the mechanics of them all. They often have a sedimentary tank where the solids are caught and then flushed out periodically. So you're losing some of the solids, so it means you're giving up some of the nitrogen, but at the benefit of eliminating sediment, which will cause denitrification to happen. So everything's a compromise, right? So once again, we want to avoid anaerobic conditions with sediments, and we need to make sure that we don't get ammonia forming in those anaerobic sections, because that can be very toxic to fish. And even if they form ammonium, not ammonia, that's this one. Remember, this is a nutrient. We talked about that in root zone, how nitrate versus ammonium. Ammonium causes soft, rapid growth in plants, which makes them susceptible to disease. Certainly, a small amount of ammonia is okay, but generally speaking, we want to have complete oxidation to nitrate, right? That's it. But so again, mineralization. This is a key term for you to remember. Has a lot to do with how much oxygen is in the system, to make sure that we don't get ammonia from fish urine to the plants and to the fish. We want to quickly move that through bacteria to ammonium, and then from there to nitrate. And if we can't do that, we need to quickly eliminate the ammonia. This is confusing. You'll have to just track my foibles. Ammonia is NH3 and ammonium is NH4. Ammonia is toxic and ammonium is a nutrient, but not ideal. It's incompletely oxidized to nitrate. One of the things about ammonia is that it's volatile. It evaporates at room temperature. If you go buy Windex, the bottle has ammonia in it. That's often used to clean windows because it evaporates quickly, leaving no streaks. So again, one of the benefits of bubbling on aquaponics system is that excess ammonia actually evaporates out the water in the bubbles. So if you stick your nose over the degassing tank, it'll smell like ammonia. So again, the part of the tank that a lot of people say, oh, you're oxygenating the tank, you're actually not. What you're really doing is you're gassing off ammonia and carbon dioxide, because they're much more of a problem. The fact that you're bubbling also adds oxygen is a side benefit. The principal reason for bubbling is to get rid of carbon dioxide and ammonia. Looking at pH, we've already talked about how pH impacts nutrient availability, but it also affects the conversion of ammonia to ammonium. So when you have a low pH, you get more ammonium, which is beneficial to the plants, at least somewhat, and not toxic to fish. If you have high pH, you get more ammonia. So everything's a compromise, right? So at the top, you're looking at fish prefer a pH range of 6.5 to 8.5. And plants prefer a pH of 5 to 7.5, although very few plants like it above 7. So you're looking at somewhere in the middle is a compromise. And so if you can try to get fish that can handle the lower pH range, you're going to get less issues with ammonia. You're going to get more ammonium and less ammonia. So once again, a compromise. We've already seen this with the nutrients, so I'm not going to spend time on that. Let's look at system design. I think your head is spinning, but you know that you need aerobic conditions, and you need to bubble off ammonia and CO2. Okay, so looking at the systems themselves, the fish are in some sort of tank or what's called a raceway. A raceway is just like a loop of water that is constantly moving, because the fish if they're sitting stagnant, it's not that good for them. Sometimes they need to exercise, right? The plants can grow anything from gravel beds to deep water culture or gutters and rafts like NFT. This is just a real simple diagram. The idea that your fish tank, the water drains out of here, goes into a clarifier or settling tank where your sediment accumulates, and then you can let it exit. And then after all the debris is settled, the water goes to the mineralization tank. This is where the bacteria do all the nutrient conversion. This is where you need lots of oxygen. This is where often the bubbling happens, or right before it. And then from here, it goes into where the lettuce and vegetables are growing. And then from there, it goes back to a tank and where it's put back into the fish. So let's look at the different components. The fish tank itself this is a very simple system where the water is circulating and the fish are just in a simple tank. What's kind of cool about this one is if you want to build it at home, you can do what's called a bell siphon. There's a link here that'll help you see how it works. But essentially, with a bell siphon, if you have a little pump pumping water up to the top all the time, the water will rise in the bed here until it reaches the height of the bell siphon, and then it siphons it all out until it's completely empty. And then the bell siphon breaks the siphon and it starts filling again. So you get your water going up and down repeatedly, indefinitely in the plant bed. And so then you can grow plants in some sort of porous media, gravel or clay balls, and they'll grow rapidly, and you'll just get lots of oxygen up here because the water is going up and down and up and down and up and down. And every time it completely empties, you get good oxygenation in the root zone. So if you want to understand how a bell siphon works and how to make one, click on that link. They're actually not that hard to make. Settling tank. This is where we get rid of solids. So typically the water goes into a tank, and in the middle is a wall, a non-porous wall. And the water hits the wall and has to travel down and around and under and then out. And this slows it down and lets heavy stuff fall to the bottom. At the college, we have a settling tank that looks very much like this. And at the bottom, there's a ball valve, and we just open it and we let solids come out. We do that maybe once a week to prevent demineralization happening or denitrification happening. The biofilter, which is where the bacteria grow, right? That's where we want to get lots of oxygen. So there's a tank here where air is bubbling up through it, and there should be some sort of structure. This one here is actually really simply just using Curly Kate dishwasher type sponge things, but you can also commercially buy these plastic sort of objects. The only thing these do is provide a surface for bacteria to live on. And the more surface area you have, the more quickly the bacteria can mineralize the nutrients. So if you just had a tank with nothing in it, really the bacteria, they don't like floating, they like being on a surface. So they would just live on the surface of the bucket, which would not be a very large surface area. By having sort of these plastic convoluted structures, we have huge surface area for the bacteria to live on. So that accelerates the process of mineralization, which is really, really critical. The degasser tank, we talked lots about this. This is where water bubbles through the tank. One of my favorite degassing systems actually is very efficient electrically as well. So instead of having a pump with an impeller, right, you have a spinning impeller that takes in water and shoots it up and out the tank. What you do is you take an air pump and you pump air down a tube, and that air goes down to the bottom of a tube that goes up and out of the tank. And what happens is as the bubbles rise in the tube, they push water with it. And so the bubbles are actually the pump that's moving the water through the entire system. So it serves two things. You're already oxygenating because you're bubbling the water constantly as it goes through the tube. and you're helping move the water slowly through the whole system. And you want to move the water slowly so that it doesn't go through the mineralization tank too quickly, because you want to make sure that the bacteria have enough time to do their magic with the waste from the fish. So bubbling a water through a riser to slowly move water through the system does the two things. It moves water through the system and degasses CO2 and ammonia out of the water coming from the fish. So typically, remember, this is after the fish. The fish are on this side. It goes, the wastewater comes in here, and then this would go into your lettuce bed. This is where the plants are. So that's the degasser. Remember, the bubbling removes CO2 and ammonia. Of course, oxygen is added, but that's the third thing. That's just a benefit. The majority of what we're doing is removing ammonia and CO2. You know I'm going to ask you that on your final, so remember that. Again, this is just summarizing a system for you. Here you've got your settling tank, so fish poop. Maybe they've got the third part of the tank has all the mineralization, plastic, convoluted structures in it, and then it goes into the tank. This could be a simpler one, right? And then here's your degassing bubbles and returning it back to the beginning where the fish are. There's a lot of different designs, and I think I had said that there's essentially as many designs as there are people out there, it seems. But the key elements are the same, right? You have fish food going in, you've got fish, you need to process the fish waste efficiently, avoiding anaerobic conditions, and then the water resulting from that mineralization goes to the plants, which then can use the mineralized nitrogen and carbon and phosphorus and potash and all that stuff, can use it to grow, and then the resulting filtered water is sent back to the fish where new feed is added, and away you go. If you're curious, this link takes you to the University of Arizona, where they do a lot of aquaponics research. Obviously, this link doesn't work on this video, but it works on the PowerPoint version that's in the same week folder for your class. All right, I hope you found this interesting, and I'll see you in class. Bye.